Good morning. Thank you for joining us for our webinar session for October 2018. Today we are looking at low carbon buildings, and my name is Katie. I look after sort of the IT side here at CABE, and I'll be acting as the moderator for this morning's session. So if there's any questions or means to get in touch, then I'll be assisting you. So talking of getting in touch, if you want to send over any questions for this morning's session, on your screen, perhaps right hand side top of your screen or somewhere depending on what device you're using to view this, there's a little dashboard and a question panel, and any questions that you want to send over, just type those in and they will reach me, and then we'll do a Q&A session at the end of the webinar itself. If you're watching on our YouTube channel, you can still send us over any questions. There's an email address on info@cbuilde.com. Pop us any questions that you've got, and again, we'll pick those up and get back to you. If you're on Twitter, hashtag CABECPD. So this morning, your presenter is Professor Phil Jones. Now, Phil is Professor of Architectural Science at the Welsh School of Architecture, Cardiff University, where he currently co-directs the Energy Systems University Research Institute. And his research area is low energy, low carbon and sustainable design in the built environment. He chairs the Welsh Building Regulation Advisory Committee and is chairman of the Board of Directors of Warm Wales, a community interest company which was formed to install energy efficient measures to existing fuel poor housing in Wales. So what I'm going to do, if you give me a couple of seconds, I'm going to hand over all the controls to Phil, and then he's going to go through this morning's sessions. So just one moment. Okay. Brilliant.
Okay, I hope I'm on. Good morning, everybody. As Katie says, my talk is about low carbon buildings, and it's an area that I've been working on for quite a while. And I want to cover a number of points. I'll start by talking about some of the targets and drivers for low carbon buildings. I'll talk about low carbon design, a little bit of history, and some examples at the end of developing technologies and some building design projects that we've been involved in. So let's start with the targets and drivers. The European Commissioner for Energy said a few years ago that people's well-being, industrial competitiveness and overall functions of society depended on a safe and secure energy system. And the EU is committed to reducing greenhouse gas emissions to 80 to 95% by 2050. And he mentioned in particular that the energy infrastructure that we're developing now is largely the one that's going to be around at that time. So it's important that we start to deal with this. We may be leaving Europe, but as far as I understand, we will still comply with the sort of directives that we have been for some time. So Europe has some targets, the 2020 targets, a 20% cut in greenhouse gas emissions from 1990 levels, and we're probably going to achieve these reasonably comfortably. A 20% of our energy from renewables and a 20% improvement in energy efficiency. On the road to 2050, there are 2030 targets of reducing greenhouse gas emissions further, more renewables and continued improvements in energy efficiency. And there are 2040 targets. So as far as greenhouse gases are concerned, we're looking to reduce them by about 20% per decade. After 2020, this becomes a challenge. The built environment is a major part of our carbon emissions and energy use. And what is proposed there is that we achieve nearly zero energy buildings for new build by 2019-2020. The Energy Performance of Buildings Directive states this. For public buildings at the end of 2018 and for all new buildings by the end of 2020. What is a nearly zero energy building? Well, it's one that has a very high energy performance with nearly zero or very low energy required, and a large amount of that will be covered from renewables. So there are a couple of uncertainties there, and these will be implemented through building regulations. I'm from Wales. In Wales, we're currently started to revise our building regulations again, and I suspect that England will follow sometime, because we have to really define what nearly zero is. So there are a couple of vague points in this definition. Very high energy performance, what does that mean? Nearly zero or very low energy requirements, what does that mean? Very significant renewables from sources integrated into the building or produced nearby, whatever that means. So I guess the building regulations will have to define how the UK, Wales, Scotland, Northern Ireland, England all have their own building regs. They will have to define what we mean by that. If we look at the impact of the built environment, commercial and residential buildings consume about 40% of primary energy in the UK and are responsible for, in Europe, sorry, are responsible for about 24% of greenhouse gas emissions. So what sort of targets will we be looking for with this nearly zero energy performance? Well, a number of countries in Europe have already set targets through their regulations and other standards, and it's likely, looking at that, that for housing, the total primary energy will be somewhere in the order of below 50 to 65 kilowatt hours per meter square per annum. And on-site renewables will be maybe up to 35 kilowatt hours per meter square per annum, with a net primary energy, the total primary energy minus the renewables of 50 to 30. And there are similar figures for offices. Now, this is from, average type European reactions to this nearly zero energy definition. In the UK, these energy targets will apply to regulated energy, probably, we don't know yet, but the likelihood is that it'll just be heating, cooling, ventilation, and lighting, so no appliance load, for example. The big question is how we will deal with renewables, whether it'll be performance-based, so that the overall performance of a building designed to the new standards will need renewables of some form, or whether renewables are going to be prescribed, that a certain percentage of energy supply should be renewables. And that's a question that we will sort of be having to deal with. So that's some background into what's driving low carbon buildings. I think it's interesting to look at the energy demand, energy supply, CO2 emissions associated with buildings, because often these are confused. The demand is for heating, cooling, ventilation, lighting. Those are the regulated demand, but there's also electrical power. And of course, this will vary with building type and location, the weather conditions and so forth. So that's the demand of energy. Now we need to supply that energy from various sources for heating and cooling, and there are efficiencies of performance then for heating systems, for cooling systems. There are primary energy factors related to the different fuel types. So different fuel types will relate to an original sort of energy at source, if you like, which is obtained by using the primary energy factors. And that's what our regulations use. We can relate that to CO2 emissions, because each of the fuels used then will have a CO2 emission associated with it. And these are the carbon emission factors. So there are primary energy factors and carbon emission factors, and they are different. Primary energy relates to the amount of energy. The carbon factors relate to the amount of CO2 emitted as a result of using that energy. And of course, renewables are zero carbon, although they have a primary energy associated with them. So there's often some confusion when we talk about low zero energy buildings or low zero carbon buildings. What is included? in the energy demand. Is it heating, cooling, ventilation, lighting, power, etc.? And how things are represented. Are we talking about demand energy, supply energy, and then there's CO2 emissions? So these are related, but it's not always straightforward. Okay, so let's have a look at the development of low energy, zero carbon buildings. We've been doing this for some time, I guess. We started looking at the energy performance of buildings back in the 1970s as a result of the oil crises at the time. There was security of supply issues. We thought the planet was running out of energy. And there was work undertaken then to look at low energy design. And low energy design in the late 70s, early 80s was all about energy efficiency, thermal insulation, air tightness, and efficient systems. And these sort of resulted in buildings that had small windows. They were inward looking, if you like. They didn't have much relationship with the outside climate. And in the 80s, 90s, we started to look at passive design. How can we use the sun, daylight, natural ventilation, thermal mass as part of our environmental solution? And this was then expanded into sustainable design around about the end of the last century, where we started to look at material use, started to look at the embodied energy in materials, started to look at renewable energy applications for buildings, and also the sort of social economic aspect of building design. You know, what is the role of a sustainable building in the community? And then the emphasis changed to zero carbon design around about 10, 20 years ago, where we reduce energy demand even further. We have a greater contribution of renewable energy. We start to look at things like appliance energy loads, and we start to look at the embodied energy, perhaps in more detail. And that continued to quite recently, and now we have energy positive design, where we can design buildings that generate more energy from renewable energy than they actually use to operate themselves. And this energy can then be exported or used elsewhere. So there's a whole sort of progression of low energy, low carbon, zero energy positive design. They all consider the same things, and I guess they really, one develops from the other. However, at the same time as this has been going on over the last 40 years, our carbon emissions have increased, now exceeding 400 ppm globally, and global temperatures continue to rise. So we know that the built environment has a major impact on our carbon emissions and climate change. We've been doing lots of research and demonstration, but the impact has been fairly minimal. So let's have a look at low carbon design and what are some of the main sort of criteria that we have to refer to. There are a number of stages when we look at the design of a building. We can think of stage one. We really have to understand what environments that we're designing for, what do the people need, what sort of processes are going on in the building. So it's to have a good idea of what goes on in the building and to try and reduce the energy associated with processes as much as possible. For example, if there are appliance loads or lighting loads, can we minimize them? Then we tend to look at the passive design elements, the climate modification. What does the building, what does the building itself do? How does it interact with the environment? How does the form of the building, the construction of the building provide the conditions within? And how can that contribute towards creating comfortable spaces? And once we've done that, we tend to look at the environmental services for heating, cooling, ventilation, and see if we can make those as efficient as possible. And right at the end now, we start to look at renewable energy and energy storage, which is now becoming of interest. So those are the various stages. We can think of at the one end there's the climate, at the other end we're trying to produce comfort, and we have a building design that has both passive and active components to take the climate and produce comfort. And we can expand that. This is something that we often use to try and put together the environmental design process. So at the one end we have the climate, and then we go into the passive design features, the site, the form, the fabric of the building. Then we go into the active design features, the environmental services, and then we talk about the internal environment. What environment are we producing, and how does that impact on people? So that's one way of looking at the process. Of course, it's not a linear process, but it's somehow useful to represent it sort of linearly. Energy features in a number of places here. We have the free energy from passive design, from the sun, the wind, from outside temperature differences, ground source, heat, for example. So these could be referred to as sort of free energy. We have the active design. What energy does our systems use for heating, cooling, ventilation, lighting? That might be regarded as the delivered energy, and increasingly this is from renewables. We also have the activity energy, the activities in the building. We switch on equipment, lights, etc. All these have an energy impact. They use energy themselves, and they also produce heat, which sometimes is useful for heat in the building, but in many cases now is a problem, and it causes overheating. And then, of course, there's the energy in the materials that's used to construct the building in the first place, and how can we minimize embodied energy in materials and products. And there's energy due to waste. When we construct buildings, we produce a lot of waste that contains energy, and when we operate buildings, we produce a lot of waste. So these are the sort of things that we might want to consider when we design a low carbon building. There are a number of issues associated with low carbon design. Glazing, solar control, glazing and daylight, insulation, thermal mass. How do we heat and cool low carbon buildings? And what is comfort different in low carbon buildings? So I wanted to just go through some of these issues and to just pick on some of them to illustrate some of these issues. So if we want to reduce heat loss, and in particular for maybe we're looking at housing, reducing heat loss makes it more affordable to heat to achieve comfort in winter, but it may result in overheating in summer. The higher the insulation levels, the less heat loss, and so if we have heat gains from the solar and from internal activities, they may result in overheating. The trend towards lightweight buildings, and in particular using timber, it's a sustainable material. This can give rise to increased internal temperatures in warmer weather or when there's high internal gains. And so we start to try to think about how can we use thermal mass to stabilize internal conditions or ensure that we've got ventilation cooling in some way. One of the problems with modern houses is that sometimes it's very difficult to open the windows for security and other reasons. So we have to sort of have that balance. If we are using a lightweight building, we must ensure that we can deal with these peak temperatures. Solar heat gains can be useful to supplement heating in winter, but when heat demand is reduced, they're often unwanted and generate the need for cooling in summer and even in winter. In some buildings, in commercial buildings, one of the problems that's emerging now is we need to cool them in winter as well as summer. There are also glare discomfort issues associated with solar gains. And so when we design a low carbon building, we need to make sure that we can control the solar gains that enter the building. We need to be concerned about not only U values of the glazing systems that we use, and we can get quite low U values now for glazing systems. Even double glazing can be around about 1. But also we need to be aware of the G value, and the G value is the amount of sun that is allowed in through the glazing system. And that's both direct gains, that the sun comes in, hits the floor or furnishings, and that gain is transmitted to the space. But with our advanced glazing systems, sometimes a lot of the solar heat is trapped in the glazing system, and that can lead to secondary gains of convection and radiation from the relatively warm internal glass surface. So we have to be aware of these, especially in commercial buildings. Maximizing daylight, we want to maximize daylight to reduce electric lighting, and that might result in larger areas of glazing, especially if we can insulate the glass and control the sun. But we do need to make sure that we do control the sun, and there's a tendency now to maximize daylight by putting the glazing, the higher levels of glazing and the daylit spaces on the north of the building. Schools, for example, probably better lit with north light. And so there's a tendency to change from the traditional lots of glass on the south to get the solar gains to glass on the north to get the daylight for certain building types. You know, however, there may be a result of this might be cold internal glass surfaces in winter. So we have to, as I said earlier, make sure that the glass is reasonably well insulated. Thermal mass provides stability for our buildings. We can expose thermal mass to the space, such as the ceiling in commercial buildings. However, sometimes these are slow to warm up in winter. So there may be a problem there, especially if there's intermittent use. So again, we have to be aware of this sort of problem. On the other hand, as I said earlier, lightweight constructions may overheat. So other issues are natural ventilation. They may be drafty at times. We might not be able to provide sufficient ventilation for highly occupied spaces, school classrooms, with natural ventilation and maintaining thermal comfort. And so we tend not to open the windows, it becomes stuffy and we have poor air quality. Mechanical ventilation can have heat recovery and can be better controlled, but it doesn't use energy and needs to be maintained. The performance of our low carbon buildings tend to be more intermittent in terms of the heating needs. So with solar gains, internal gains, we can see the bottom right graph there, the solar gains that come out in the day, the black vertical lines represent the heating energy, and the boiler turns off when the solar gains are there. And so we have to have heating systems that can deal with intermittent use, and this is potentially more problematic to control. So the smaller the heat demand, the more difficult it is to control. Another example of a school classroom where we can see that the incidental gains from people and equipment, the orange, dominates the energy delivered to the space. The solar gains build up as the day progressive. It's a northwest classroom, so it tends to get afternoon sun. And we can see that the heating system only comes on in the morning to warm the building up, and maybe at lunchtime after people go out of the building. So we have this more complicated control strategy that we have to deal with. Another of the issues is with new build, with new low carbon buildings, is how do we heat and cool? Is the solution electric, which we're sort of increasingly led to believe, and the role of heat pumps. Air source heat pumps are not very efficient in summer, around about COP of maybe 0.15, or some of them are becoming more efficient now. Ground source, where we've got a higher temperature source, the efficiencies of 350 or COP of 0.35. If we can somehow store heat and use the heat pump to extract that heat from the storage, then we can get very high efficiencies for heat pumps. And this is an area that is currently of interest. Can we collect heat, store it, and then use a heat pump to heat the building? And to some extent, this works for cooling as well. Another issue is how do we provide comfort in low carbon buildings? Is it the same as more traditional buildings? Do we deliver the heat through the air with air systems, or through surface systems? Do we heat up surfaces? Just to follow this up, with commercial buildings in Europe, the tendency now is to heat and cool with surface systems. And in commercial buildings, cooling is probably the main issue. So we can use thermal mass combined sometimes with active cooling, chill ceilings, chill beams, to produce the main cooling, to deliver the main cooling to the space. So we decouple the cooling from the ventilation system or the air conditioning system, which means the ventilation can be much less, just providing air for breathing and not for getting rid of lots of heat gains. So if we follow this up, if we look at the traditional way of providing heat and ventilation for commercial buildings in this case, internal gains traditionally quite high, solar gains quite high, huge air change rates with air systems to get rid of all that heat. So the thinking is, and very often then we need to recirculate the air because we don't want to lose the coolth or the heat that we've delivered to the space. The first step in any low carbon design is to reduce the internal gains. And for commercial buildings, we tend to try to get to 25 watts per meter squared. And that's for people and equipment and lighting. Then we can use a smart facade, multiple skin or with shading, to reduce the solar gains, to have a low G value, and so reduce the solar gains to around about 10 watts per meter squared typically. Then the ventilation is less. We reduce the ventilation from an all-air system to just providing fresh air for breathing. That's 100% fresh air. We don't need to recirculate. And then we use surface cooling, either exposing the thermal mass and getting rid of that heat at night through nighttime ventilation, or we use active thermal mass. We chill the ceiling with water, and we can get about 30 watts per meter squared plus of cooling there. If we have higher heat gains, we can use chill beams, which give us more cooling. And so this is the way that our thinking is going on, how we deliver heat and ventilation to commercial buildings. So we can have exposed thermal mass, active chill ceilings, active chill beams. And these have multiple benefits: lower fan power, higher cooling COPs, because the temperature of the cooling medium is higher than it would be for air. We have better air quality, no recirculation. We have easier air distribution to the occupied zone. We don't have so much air to push around. It's more comfortable. Less space for equipment because we don't need, so the ducts are smaller, the plant is smaller, less space for distribution, reduced floor-to-floor heights, greater space for occupants. We can occupy the building up to the window edge because we've got smart glazing, and more stable conditions in general. So this is just an example of how we might take things forward for how we deliver heat and cooling and ventilation to our buildings. Right, I thought it might be useful to have a little bit of history before I go into some examples. I've been working in this area for a long time, and the first building project I worked on was the Abertrydydd Better Insulated Housing Programme, which was late 70s, early 80s, where we monitored intensively 20 houses that were better insulated and compared it to 19 houses built to the current standards. So U values were quite high at the time for current standards, and it was the first time that we started to put thermal insulation into walls. So these houses, the project was funded by the government as part of their sort of reaction to the need to have to reduce energy in buildings with the the oil crisis at the time. And it was one of a number of similar projects throughout the UK. And we were able to show significant energy savings due to this thermal insulation. We were able to start to understand the way solar and internal gains affected the space, affected energy use, and also started to look at heating system efficiencies. Also, we did a lot of thermography work. We were able to identify problems of design in getting the insulation into the fully integrated into the design, design and workmanship problems, where insulation was missing and what was the impact of that. And also, excuse me, we looked at air leakage, and we were getting air leakage rates up to about 8.5 meters cubed per hour per meter squared, which is not too far out. Well, it's similar to the sort of current requirements. However, when we went back 2 years later, that had almost nearly doubled because of the settling in of the house. And the project was also used because it was a lot of houses being monitored. The windows, some of the windows were replaced with Capafolk glass in collaboration with Pilkington, so they tested Kappa floats in Abertrudu, and trickle ventilators started to come in, and Titan trickle ventilators were tested there. So we learned a lot from the building, from this project, and it was used to inform building regulations at the time. And the question is, you know, how far have we come since Abertrudu in our understanding of low energy, low carbon buildings? So that's what I wanted to go on to finally, was where are we going with technologies since Abertrudu over the last 40 years, probably nearly, and how are we designing buildings now differently that meet low carbon requirements. So the first thing I wanted to do is to talk about renewable energy, because since the early projects, renewable energy integrated into the buildings is probably the biggest development. And here we've been looking since around about 2000 at how we integrate renewable energy generation into building facades and building components. At the top there, we've got PV used as shading in a factory in Wales, where we designed the factory in the Welsh School of Architecture here at Cardiff University. It achieved a BREEAM Excellent. I think it was the first industrial building to get BREEAM Excellent. It won a design award, and it's sort of demonstrate how we can use renewable energy, not just bolted onto the roof in the form of PV panels, but to provide shading as well. So it does two jobs. At the bottom, we can see in the middle there, the green building. That was a building that we worked on with Tata and the Welsh Government. It's Tata works in Shotton. And in this case, the building envelope collects solar heat through the panel system. That's a south facing elevation, areas drawn in to what is called a transpired solar collector, and then that's used to heat the building. So we're actually using the envelope of the building as an energy generator. We also did another project funded by the Wales Energy Funding Organisation or Office, WEFO, and that's B&Q in Merthyr Tydfil, where we've put the transpired solar collectors on the roof. And these are monitored, and they show that we can get a significant amount of energy from these systems. So these were some early projects that we did this century. The factory in 2000, I think, finished in 2001, and the Tata research building finished in 2010. More recently, we've been applying the transpired solar collector in any case, and solar PV, although the solar PV in this example is just on the roof. But that red wall there at the end of that building is a public building in Lhasa in Tibet. And about 2 months ago, we opened this building, and that uses a transpired solar collector to heat that building in Tibet, where they actually have quite a bit of sun. and we're looking at other buildings in Tibet at the moment. This was carried out in collaboration with Xi'an University and Lhasa University in Tibet. Another project that we're looking at the moment, a development, is a European project. It's called Plug and Harvest, and here we're looking at facade systems that can be applied to retrofit mainly, but also new build, that have a layer of technology, if you like. The first layer, the outside, is the renewable energy generation. That could be PV, or it could be air collection, solar air collection. There's a technical zone, and there's an insulation layer. So the sort of low energy design is in the facade. So we can insulate, we can have PV generation. In the technical zone, we can locate battery storage. We can have thermal air heating in behind the sort of the PV layer, and we can also incorporate mechanical ventilation, heat recovery. So it's all in the facade of the building, and we're testing this building on a range of commercial and residential buildings across Europe. So these are some developments in how we can deal, in particular, with renewable energy and integrate it into the architecture of the building. So we like to think of a holistic approach to our design. And before I go on to a couple of examples, this is the sort of method we adopt. Firstly, we reduce the energy loads in the building, low energy lights, appliances, etc. Then we look at passive design, orientation, mass form, fabric glazing. Once we get that right, we do as much as possible with the architecture of the building, and then it makes the heating, cooling, ventilation, lighting simpler and more efficient. And of course now, because if we can reduce the energy demand, renewable energy becomes a bigger part of the energy solution. And now, of course, we're looking at building integrated renewables plus energy storage, battery storage, and thermal storage. So this is the overall holistic approach that we try to use. And I want to look at two examples. One is a house. This is a Solcer House. This was funded by the Wales European Funding Office as part of the Low Carbon Research Institute program, which took place from around about 2009 to 2014. And at the end, we managed to fund a demonstration house, a test house, which uses a systems approach to reduce demand. So it's nearly passive house performance. I say nearly because we didn't go for accreditation because we wanted to use local supply chains and materials, etc. And it includes renewable energy supply, both in the form of the solar PV roof and the transpired solar air collector wall. And we have energy storage in the form of domestic hot water and battery storage. And what we wanted to do was to make sure that we can achieve an energy performance. In this case, we're going for energy positive. We want the building to generate more energy than it uses. We want it to be replicable, and we want it so that anybody can build it, and we want it to be affordable. And this is the main thing, to design a house like this that is not that much different from a standard house type. And that was our main target. We wanted to integrate the systems, so we want to integrate the thermal and electrical systems. So the PV panel and the battery storage drives a small heat pump. The house is heated through the ventilation. The energy demand is so small that we can do that. We take the extract heat. The heat pump takes the heat from the extract and puts it into the supply. So we're not operating on outside temperatures, so the COP is relatively high. And also we wanted to integrate the technologies into the design of the building. So that's the basic philosophy behind it. There's the roof system. The roof is the PV panel, and the roof space is daylit. The transpired solar collector is the external first floor wall finish. And so they become integrated the generation of energy is integrated into the architecture. The ventilation heat is then delivered to a Genvex combi heat pump. That provides mechanical ventilation heat recovery and also water storage. It's around about 500 watts, so it's quite small. And we have battery storage. We have 6.9 kilowatt hours of lithium ion. And that really provides enough energy to take us through the night to the next day. And of course, if the sun doesn't come out, we import from the grid. So the priority is to use the renewable energy directly for lights, appliances, then to charge the batteries. Then we want to heat domestic hot water. And if there's any left over, we export it to the grid. The house is constructed from a SIPS, structurally insulated panel system. It's highly insulated, airtight, recycled timber. It went up very quickly, 16 weeks for the whole of the construction program, either side of winter, so conditions weren't perfect. And the estimated cost is about £1,200 a square metre, which is acceptable for social housing, very much acceptable. And it achieves an energy performance, positive performance. A typical new house might use an estimated £780 a year. We actually earn by exporting excess energy 166. So the benefit to the householder is nearly £1,000 a year. And that's really quite big for social housing. This is the amount of energy on a monthly basis, so the amount of renewables that's used in the building. This is how much we export from the grid in the winter, and mainly in the summer we export to the grid. So we have a grid power to and from grid ratio of 1.5. It exports 50% more than it imports. And the self-sufficiency, the building is able to operate by itself outside of the grid for 3/4 of its time. We've done a lot of surveys. We've asked people what they think about it, and people like it. In fact, the usual comment is, why haven't we got a house that's energy positive? So the other project I'll talk about is an office. We've done a lot of office buildings, working on low carbon design. The bottom two on the left in Switzerland using smart facades. The one to the right, the taller one, is in the Hanover Trade Fair, Hanover Expo, sorry. Again with an interesting facade and ventilation system. And the one on the right, it wasn't built, but we did that with Atkins in Dubai. We did the building physics. Unfortunately, the economic crash came in it. Although they started construction, it wasn't finished. But what I want to talk, oops, gone the wrong way. What I wanted to talk about is this one, because it's an example of how we bring things together in low carbon, low energy design. It's got a facade. The blinds are glazed, they move with the sun, they let daylight through, but they keep the direct sun out, so they minimize cooling. It's got an atrium, which is used as part of the ventilation system. So at night, the building is cooled through drawing air in through the offices. It's an office building, through the offices, up through the atrium like a chimney, and cool the exposed thermal mass at night. In the day, it's mechanically ventilated by drawing the air through a set of pipes in the ground, and that gives us quite a bit of cooling. When it gets to about 35 degrees in Zurich in summer, the air coming out of the ground is about 27, which combined with the nighttime cooling of the thermal mass gives us a comfortable building. It's got a bit of heat recovery from neighboring processes, and it's got some renewables. This building was designed back in 2003. We did a lot of the building physics on this. We did a lot of computer simulation. It was occupied in 2005, the first time, I think. And the simulations that we did were borne out by measurements taken in practice. So the computer models that we use to design these buildings, we're fairly confident they work. And the demand can be really reduced from a standard building. The red is heating, blue is cooling. The green is electrical power. The grey is the embodied energy in the building construction. So if we go to the extreme right, which is our building, it practically uses no energy. It's interesting that the operating energy normalized over the lifetime of the building, is now of the same order as the energy it costs to build the building. So we have a range of performances: low carbon, nearly zero energy, energy positive, and we can't achieve energy positive for all our buildings. The high-rise 400-meter building is very difficult to make energy positive. So we do need energy coming in to the built environment, and our future grid is going to be decarbonised, but also we need to start looking at our energy infrastructures. I think new build, we know what to do. The big problems now, and I haven't spoken about these days, is retrofit, and that occupies much of our time these days, and how we implement low carbon, nearly zero energy at urban scale. And if you look at the big research funding in Europe, that's where it's going now: retrofit and urban scale. New buildings, we don't worry about too much. We think it'll continue to develop, but for new build, I think we know how to do it. So some finishing thoughts. We know how to do it, we think. The question is, why haven't we made more progress over the last 40 years? The construction industry is slow to change, it's very conservative. You might even say it resists change. And so we really need to get the construction industry taking low carbon seriously. Who owns low carbon design? Is it the architect? Is it the engineer? The building physicist? If you go to Europe, he's part of the design team now, and that's what pushes things forward. The project manager, and if we're in a design build situation, it's still lowest capital cost that rules the day. So it's very difficult when you go into a design team to get anybody to really own the problem. End user awareness is very little of that around. We've experienced that with the house we designed. When people come there, they say, we didn't know this was possible. Volume house builders will tell us people don't want low carbon buildings or zero energy buildings. But you've got to ask the question, are they aware of what is possible? And then when we look at procurement of buildings, we're often locked into standards and frameworks and processes that again resist change. They protect themselves against change. So what do we need? So, well, for new build, we've been doing demonstrations for 40 years. And the answer always seems, what are we doing about low carbon buildings? We'll do another demonstration. We've had enough demonstrations. We really need to mainstream low carbon now. Otherwise, we're just pushing the problem into the future. We need to look at retrofit and urban scale issues, but we know enough about new build to make low carbon buildings mainstream. So thank you for listening.
Excellent. Thank you very much, Phil. That was a really interesting session this morning. What I'd like to do now is if anybody has got any questions, to send those over, questions or comments, anything like that. And I'll just give it a couple of minutes and then we can put those through to Phil. Whilst you're doing that and considering those, I just would like to let you know that our next session will be held on the 21st of November. 8 AM as usual, for those of you who are familiar with our webinar Wednesday programme. And we're going to be looking at the retrospective application of BS 9999. So there will be a link to register for that in the email that you'll get after this. So please feel free to join us and let everybody know that your colleagues know that that session will be taking place. So coming in now, Phil, we've got something coming in for you. Are there any plug and harvest claddings on the market currently for retrofit that you're aware of?
No, not well. The plug and harvest is a new product, so there are things like the transpire solar collector, which are sort of do part of the job, but I'm not aware of anything that does the whole job. I think of course, the plug-in harvest will vary depending which facade you apply it to. You wouldn't have a PV layer on a north-facing wall, for example. And there are some products that just, I think, do the insulation as a plug-in. But I'm not aware of anything that tries to sort of be to do the whole insulation, renewables, battery storage, ventilation. No.
Okay, thank you. In terms of questions, that's really all that's come in so far. There's a few comments coming in, thanking you for your time and just saying that, you know, the presentation was really interesting and it was an excellent presentation. Yeah, loads. Oh, here we go. Let me just have a look at this one that's just popped up. Right, okay. So it would appear that there is research funding going up to at least 2021 coming from the EU. Will research money still be available after we leave the EU?
Well, it depends on the deal.
Yeah.
What we're hoping is that if there is a deal, then we will be able to access European programs. Whether we'll be able to access the funding or whether we'll just be affiliated and we get our funding directly from the UK. It all depends on what sort of deal is done. At the moment, we're secure up to that time, but we do hope that there will be some solution.
Yeah, sure. So it's all very up in the air, isn't it? So,
yeah.
but again, that's all we've got in so far. So, like I say, what I think I'll do, I'll wrap it up there. But again, if anybody does have any questions, or if you think of anything that you want to bring up, then pop me over an email and I'll liaise with Phil and we'll get a response to you. So again, it just remains me to say thank you for your time. Thank you for joining us. Thank you to Phil for the presentation. Again, see you hopefully online next month. But as I say, this session is being recorded and uploaded to our YouTube channel, so you can catch up there and share it again with colleagues. And you can claim 1 hour CPD for this morning's attendance. So thank you very much. We'll see you online again soon.
Thanks, Katie. Thanks, everybody.
Thank you.